Hello, everyone, and thank you for being here with us today. My name is Michelle Amiot, and I'd like to welcome you to today's webinar, Configurations and Applications of Solar Electric Systems. This webinar is sponsored by Solar Energy International and broadcasted by Informa. I'll be your host for today's webinar. Before we begin, I'm going to take a minute to orient you to the webinar platform. First, we recommend participating via Google Chrome for the best experience. Secondly, this webinar is designed to be interactive. There are widgets at the bottom of your screen that will allow you to learn about today's speaker, download resources, and share this webinar via social media, and participate in the Q&A session. You can use the Q&A function to ask our speaker questions, which we'll do our best to either answer directly or live at the end of the presentation. We have quite a number of people with us today, so my apologies if we don't have time to get to every question. For the end of our webinar, we're going to ask you to complete a survey, which will be found on the right-hand side of your screen. So please help us with your feedback by filling that out. Lastly, if you are experiencing any technical problems, please click the Help widget that is also found at the bottom of your screen. Alternatively, you can type your issue into the Q&A area, and we'll do our best to offer you one-on-one assistance. Now we're about to get started with our presentation. Our speaker today is Christopher Sutton. Hello, Chris.
Hello there. Thanks, Michelle.
Yeah. Christopher Sutton is the director of the Middle East and Africa program at Solar Energy International. Christopher has been working in the solar industry for over 20 years as a lead technician and designer. Through his work at SEI, he has trained more than 3,000 people and now focuses on training programs in the Middle East and Africa. So now, Chris, over to you.
Thank you.
Hello, and thank you for joining me today for this webinar provided by Solar Energy International. My name is Christopher Sutton, and I'll be your instructor for this course. Solar Energy International, or SEI, is a solar technical training provider. We offer courses through various formats like online, in-person classroom-style classes, and hands-on practicals at various training centers throughout the world. SEI has been in business since 1991, and we've had over 76,000 alumni through our programs. We're trying to support a growing solar industry throughout the world. We began in North America, but have been doing trainings in Central and South America, the Middle East, and Africa regions. We started training in the Middle East about 8 years ago, and we've been offering various courses with partnerships that we've established in a number of different countries. We also have created a hands-on facility in Muscat, Oman, where we can do 1-week classes where people learn how to install, commission, test, do performance evaluation, and do all the parts of basic installations on multiple systems that are on that site. Our classes also provide support for a number of certifications, specifically in Oman and also Dubai, that help go towards various local certifications. And we have a big team of instructors that we work with from all over the world with different skill sets and backgrounds, so they can bring a lot to the table with all of the practical knowledge that they have in the field. All of our instructors are solar professionals first and instructors second that come in and help work with SEI to provide technical training. In this course today, what we're going to get into is talking about the applications, and we want to start to think about what are my customers' needs? What do I need to do to provide a system that's going to meet the goals of this site? And so we're going to go through a lot of things. We're going to start by talking about DC and AC electricity, so we know what part of the electrical system that we're working in. We're going to talk about what are the different components that go into making up a solar electric system, for what purpose. And so we'll get into a lot of different system types and styles, and really kind of electrical architecture to determine what type of products we need to specify for what system types. We're going to go through what we put into categories of like 4 major kind of applications, but as you see, we'll that solar is able to do a lot of different things. And so we kind of have a lot of subcategories as well. But the big categories, we start to put things into what we call PV direct, or solar running something directly without any control or storage. Standalone, meaning something that's off grid, that's not utility connected, that is an independent power system. Grid direct, when we say that, we mean something that's going to synchronize with a local utility grid and backfeed power or connect to the grid whenever the grid's available. And then multi-mode system is a system that can work as a standalone system or a grid synchronizing system with a lot of versatility. We'll get into some of that. And then we're going to look at a number of kind of flow diagrams, thinking about energy flow through a system. And so we can understand what roles the components have and how does the energy run through the different system types. We're going to start just by understanding that we have two types of electricity. Now, I know a lot of you are probably engineers on here, but just as that reminder, we have DC and we have AC electricity. PV modules or PV cells are a DC device. Same with batteries. Batteries are also DC based. So whenever we're on the battery side or the PV side of the circuits, we're going to be operating with DC electricity. We also have, of course, AC electricity. So alternating current is the way that all of our utility grids operate. Powered, all of our gas and diesel generators, wind turbines, hydro turbines, all those sorts of things are mainly AC devices. And so we live usually in a situation where we're going to intermix DC and AC in our electrical system. So we just have to understand what we're talking about and in what part of the system. Now, the first thing we have to think about in all of our electrical systems are, if we're designing a power system, we need to understand our loads. And what are we going to run? How long are we going to run it? We got to understand the loads first so we can design the system. So step one is start to think about our loads. Are we running DC loads, AC loads? Are we grid synchronizing? What are we going to run with this system? So that's the first thing we got to understand. Now, if you're new to this, photovoltaic is the technical term, which photo means light, voltaic means voltage. We're turning light into voltage or light into electricity. We often call that a PV module. PV module or PV panel. And you can see the electrical symbol. If we were in like an AutoCAD drawing, you would often see PV modules with that electrical symbol. So the PV module is really the powerhouse, the generator of our solar electric system. So that's where we're going to get DC electricity, and we're going to put that to whatever the next thing is. So we'll start with the solar modules and work our way from there. Now, if we think about what is kind of the most basic and the most simple, fundamentally, system type in a way, it's what we would call a PV direct system. And there's not a lot of applications for this, but there's a couple that are very specific. PV direct, when we say that, we mean we're taking the solar modules and the DC electricity is going to directly run a load with no storage, with no inverter, no controls. We can run PV to something, in this case, like a DC water pump, for example. So we could run a well pump or a pressure pump or some sort of a surface pump with, as long as, of course, it's a DC motor, with the correctly sized PV array. And so if we have a system like this, it's a PV direct with no battery storage and no secondary controls or anything, then a system like this is a daytime use only situation, which that could work great for a lot of things. If we can pump water, let's think about maybe agriculture, for example. If we pump water just during the daytime and store it in tanks for animals to drink from, that's a great use of daytime only pumping. We could also pump water and store it higher up in an elevated tank or cistern in a place that is, up a hillside or on a mountain, maybe for a village. and then gravity feed that water back down. So we have to understand the limitations of this are daytime only, um, but it's also very simple and it saves a lot of money if we don't have to have batteries uh, and a lot more, maintenance, troubleshooting, costs, things like that. Now, there are actually a number of specific inverters on the market today that can do PV direct water pumping to an AC three-phase pump motor as well. So that's another PV direct application where we could end up with AC. So that's kind of our basic system. It's a bit limited in its application, but for the right thing, it's maybe the cheapest way to solar power something like a pump load. And then, of course, as I said, at nighttime, when the sun goes down, we will not have any output of that system. Now, if we say, okay, we're going to stay in this off-grid category for a little bit, and then we'll get to grid connected later in the lesson. If we say, okay, I have solar and I want to run something, but I need something to run 24 hours a day. I need storage on my system so I can have surge loads, things like that, and have nighttime energy. So anytime I need to do that, I need to put storage in like a battery. So we're going to put a battery into the system. And anytime we put a battery into the system, we also need to put in a charge controller or a charge regulator, something that's going to manage the solar charging into the battery. Because when the battery gets full, we need to turn the solar off and basically let the battery rest until either a load comes on to pull the battery bank back down. We can damage the battery by overcharging it. So we need somehow to manage the solar to battery interaction. Now, it doesn't matter if this is lead acid or lithium or whatever, they all have their own way that they need to be handled and set points that need to be managed by the charge controller. So we use the charge controller or charge regulator to manage our battery banks. Now, in a basic system, we're talking about a DC only system right now. We'll get to adding AC shortly. So in a DC only system, we now have PV array, we have our charge controller, our battery bank, and our DC load. So the charge controller sits between the PV array and the battery bank, and it is able to turn the PV array off when the battery is full. So PV array is our source of generation. Charge controller is our regulating device. Battery bank is our energy storage, and then we have a DC load. Daytime system, the battery bank will charge up and hopefully get to full if it's all sized right. And then when the sun sets, we'll drain the battery down based on whatever the load that we're running. So now, sometimes we can get a different type of charge controller. So this is a charge controller that also has what we call a load controller. The load controller is a way to manage the loads, not only for if the battery gets too full, but also if the battery gets too low. If I actually go back to this last example, in this type of system, if I pull a load directly off the battery bank, I can pull the battery down to a damage level if I don't control it or monitor it somehow. But if we left the load on, we could hurt the battery bank. If we wanted to do that another way, we could use an integrated charge controller, load controller combination. And now these are sold as smaller devices, often designed for small off-grid systems or lighting control systems, but small applications generally with an integrated charge controller and load controller. So then that protects the battery from being too full, or it protects the battery from being too empty or too discharged. Now, if we want to add an inverter to the system and we say, okay, I need an off-grid system, but I want AC loads as well. So to have AC loads, we need an inverter. An inverter is going to turn DC into AC for us. there's a lot of different sizes, types of inverters on the market. And so we have to understand that when we say an inverter, really it's a DC AC conversion. And there's a million different types of inverters for different purposes. And so we have to understand the purpose and the type of what's out there to make sure we're buying the right thing for the application. There's also a lot of different sizes too. We have very small ones that we call a micro-inverter. We have mid-size inverters that are in the maybe 2 kilowatt to 100 kilowatt range. And then we have what we call central inverters, which are usually our bigger, hundreds of kilowatts to multiple megawatt big single unit inverters. So we have different sizes based, of course, on our scale and application. So now if we take and we stay with the idea of a standalone system, something that's off-grid, independent system with AC only loads, then what we've done is we've taken that basic battery system that we started with. PV array goes through the charge controller. Charge controller connects to the battery bank so we can charge the battery with that solar power. And then the battery bank discharges through the battery-based inverter. So this inverter would be a battery-based, off-grid, standalone type of an inverter. And then at that point on the right, we are at an AC output now. So now we have an AC output for that system. And we run that into an AC distribution panel or MDB, whatever our load is and our distribution from there. So PV array does the generation, charge controller regulates the PV, battery bank is our storage, and now we've added conversion of DC to AC and consumption in our main distribution. So that's our standalone AC only type of system. Now, there's some applications out there where we might want DC loads and AC loads at the same time. And so with this slide, what we're seeing is just the ability to add DC loads off of the battery. And if we do put DC loads from the battery, we want to use what we call a load controller. So we don't take the battery too far down by pulling DC direct. And so sometimes there's industrial applications or telecom or marine situations where you might have DC and AC loads on the same site. And that's totally easy to do as long as we protect that battery bank with a DC load controller. When we have a battery-based inverter, if it's a good quality inverter, we can set points in there to act as a load controller on that side. So we can tell the inverter to turn off if the battery bank gets below whatever we set it at, 50%, 20%, whatever, whatever the number is based on the battery design itself. So we just want to know that we got to protect our batteries from overcharge and over discharge to make sure they last as long as possible for us. Now, the difference here in this slide is we've added an AC source. So let's say we have a off-grid or standalone system, and we've decided that we want to have a backup generator on that system as well, because we know the sun doesn't shine every day and loads can fluctuate, and we need to make sure that we, during the short days and the long days, can produce as much power as possible. So having a backup generator is always a good idea as the systems get bigger or more important, more critical, depending on what we're running. Now, the difference here is that in the previous slides, we were looking at what we called a battery-based inverter. Now we've changed to a different type of product, which we're calling a battery-based inverter charger. Inverter charger means we can now, instead of just go from DC to AC, we can also take an AC source and act like a battery charger and charge the battery from an AC side. So it has the ability to run both directions now with this inverter. So DC to AC or AC to DC. those inverters will have a separate input for the generator most of the time. And so you can have a generator as what we might call an AC input, and the main distribution as the AC output of this battery-based inverter charger. So, and with good quality inverters too, we can also do auto start. So if we have generators that are auto start capable, and we usually do once they get into any real size other than small generators, if we have auto start capable, we can tell the inverter to start the generator whenever it needs to charge the batteries at a certain set point. And that allows a lot more protection and oversight in the system, that we can maintain the battery at the state of charge we want all the time. We can minimize generator runtime by putting enough solar in, and we can have constant and stable supplies of electricity. Now we're going to shift gears a minute, and we are going to look at a grid direct system. So in all of our previous examples, we were talking about systems that were off-grid or remote or isolated standalone systems. Now we want to look at a grid direct system where we're taking the solar, we're turning it from DC to AC, but we're also synchronizing that with the electrical grid or the electrical utility. So we're going to start by thinking about, we have a different inverter now. This is completely different than the battery-based inverter chargers we were just talking about. It does DC to AC, but this inverter does a lot more as well. It does auto synchronization to the utility grid. So we need to make sure that we're selecting inverters with the right voltage, frequency, single phase, three phase, to synchronize with whatever utility voltage and frequency that we have on our site. And we can get grid synchronizing inverters in all standard voltages and frequencies throughout the world. So the next thing that happens, we go DC from the PV array into the inverter. The inverter, when it sees AC electricity from the utility grid, it will synchronize with it automatically, and then it will basically, once it synchronizes, which it can happen in seconds because it's electronic synchronization. This is completely different than trying to synchronize a motor generator. And a lot of people think about these things like a motor generator, like a diesel or propane or gas generator. And this is very different. An inverter like this doesn't actually produce its own voltage. It just synchronizes with the voltage and frequency that it sees on the utility grid. And so when you put DC in, it doesn't create an AC output by itself. That concept is something that we call anti-islanding. Anti-islanding means that this inverter will not create a voltage if it doesn't see a voltage from an outside source. So this inverter has to see voltage and frequency on the AC side, and it has to see voltage on the DC side from the PV array. And unless it sees those three things, this inverter will not start up. So it has to see a stable grid and stable DC voltage. Then once it sees that and it recognizes the voltages and frequencies are within its operating window, the inverter will synchronize and push AC output into that AC electrical system. So at this point, the inverter's on and it's operating. PV's coming in, AC is coming out. We're going to go through the next thing to the right, which is a meter. So a lot of utilities want to see a secondary meter. The inverter itself has a meter on board, and so you can get readings off the inverter, of course, of its own production. But often utilities will specify that they want a secondary production-only meter. So that meter is measuring the total output of the AC side of the solar electric system. Now, the next thing we see is main distribution. So we have the consumption part of our system. So that is where we're going to inject the solar output into the electrical system and make what we call our point of interconnection to the utility grid. Now, if this is on um, a situation where there are loads, electrical loads on site, like a house, a residential system, for example, a small commercial business, everything up to a factory. Anytime we have loads on site, we're going to connect to that load distribution panel somewhere. And now we have the ability to feed those loads, the on-site electrical loads, from solar and from the utility grid together. So all of that electricity is synchronized in that main distribution panel and able to feed our electrical loads when the solar is available. Now, where that energy goes is going to be dependent on how much solar output we have. So how many watts or kilowatts or megawatts is the output of the AC side of our solar system, and how big is the solar array, and how sunny is it? Those are all going to change the output. So the output of the solar is going to change throughout the day based on the amount of sun and size of the system. So depending on the output of the solar in kilowatts or megawatts and how big the electrical loads are in the building, we may either just feed the electrical from the solar direct into the building and have no additional from the utility grid, or if we have excess solar, we can push energy back into the utility grid, and that goes through a secondary meter there. And that secondary meter, or that's actually really the primary meter, let's say, for the buildings. That would be your normal building meter. And then, so we can measure the input and the output to the building. And then once we go through that meter, then we go to the electrical grid itself, the transmission system, through a generator or wherever it goes as it enters into the electrical grid. So if we kind of think our way through here, then again, we generate energy, we convert it DC to AC, synchronize it to the grid, we measure the output of the AC side of the inverter. We either consume the energy or we export the energy out into the grid. And that's why at this point now, we see that we have these arrows on the right side of distribution that go both directions, because we can export to the grid or bring power in from the grid based on how many kilowatts we're producing versus consuming. So that part of the system, we can send energy both directions. Now, in order to send energy both directions through that utility meter, that utility needs to replace that with what we think of as a bidirectional. Bidirectional means, it really means that it's been calibrated and tested to run both directions and measure accurately in both directions. So that's our bidirectional utility meter. And that's often what we would call a net meter too, because it just sees the net difference between import and export. Now, the other thing about this system, this type of system, this assumes that the utility grid will allow us to push power back into it. So that becomes specific to the utility company or government or municipality or whoever oversees the electrical distribution company. So there's going to be what we call an interconnection agreement, some sort of a way that we agree on the price and the value of that energy that comes out of the solar and into the electrical grid. A lot of places still around the world will not allow interconnection to the grid, so we have a few other ways that we handle that, and we'll talk about that later in this lesson. We can also get into systems with multiple inverters as well. It doesn't have to be a single inverter. We can put a lot of inverters in parallel. We see that a lot too. So one of the things we have to understand about this inverter and what's so different about it is we don't have a backup power system here. This isn't backup power. So there's no storage. We don't have a battery. and we have an inverter that only produces AC power when it's synchronized with a utility grid. So when the utility grid fails, if we have the grid go down and we lose our AC supply from the utility, our inverter is also going to go offline. These inverters are designed to not push voltage into a dead utility line. And we don't have any storage anyway. So this system is designed to shut down when it loses AC power. Now, that's a safety thing, of course. And what we're really trying to do, and what we have to understand with this type of system, that a grid synchronizing inverter connected to the utility grid, we can only use if we have a utility that allows interconnection, and we have a utility grid that's relatively stable, because anytime the grid goes down, this inverter is going to shut off. And so it only really works well with a good quality, stable electrical grid. So that's really going to depend on the utility company and country location that you are. So we have to understand those things. Now, if we need backup power, since this is not a backup power system, we can get into other options for battery-based backup. But this is the simplest, highest efficient, usually lowest cost way to interconnect solar into the grid. And that's why even without backup power, it's really the most common type of system installed in the world today. Now, when we take the output of that system and we connect it into the grid, this is just showing a couple of photos and understanding that we're measuring things with our meters, and we're using electrical service or electrical distribution panels to move all this energy and interconnect together. This is just a photo of the inside of an AC residential electrical distribution panel. And the service entrance of the utility conductors are coming in from the bottom. There's a main disconnect right there, or a main isolator. There is metering or measurement right in the middle. We have two big load circuit breakers that split off to two sub-distribution. And then on the top, we have a PV circuit breaker that ties in. So the PV and the utility all meet on the same bus bar and match voltage and frequency automatically by the inverter. So that point of interconnection with the utility is actually not very complicated because it just synchronizes and connects to the distribution through a normal circuit breaker. So just thinking about kind of where energy flows through the system, it can either run from the PV to the loads, or if there's more solar than the loads, we can push right through and out through the service entrance conductors back out to the utility grid. So that's kind of our inner way. That's the way a basic residential interconnection might look. Now, if we talk about big solar power plants, solar farms, multi-megawatt, or these days getting into gigawatt-sized solar plants, really, it's the same concept of what we just talked about with the grid direct system. Those big solar power plants, unless they have batteries with them, those inverters work exactly the same way. And the way we configure the solar arrays are also exactly the same way, just much larger. So we go to what we call a central inverter. Central inverters we use when we get into big, tens and hundreds of megawatt systems. Central inverters today are getting up to, they're over 2, sometimes maybe getting close to 3 megawatts per unit for big central inverters. So maybe 500 kilowatts to 2.5 megawatts. That's kind of the normal central inverter range. And so then we're just putting megawatts worth of solar to match the inverter input. Going out of the inverter, AC synchronized to the grid. In the same way, it does the auto synchronization because it's not like a motor generator. It's a solid state piece of electronics. And so it automatically synchronizes with the grid. It doesn't make its own voltage. It does the same thing. It synchronizes with an external voltage. And then when we're making energy, then we'll push through a meter and we will go right into a transformer and up to whatever the interconnection transmission voltage is there. So of course transformers get sized to match the inverter voltage to the transmission voltage in the area, but it all works the same as the smaller grid-tied inverters. They're just larger. And the only difference with a big power plant is that we don't have loads on site. We're just measuring all that energy and putting all that solar straight out into the utility grid. So it's basically just a big version of the same what we might have in a residential system. The way it functions is just larger, of course. Now, one thing that we're seeing happening with big solar farms, big power plants, is the ability to connect batteries in there with it. As we get into larger and larger amounts of solar in the world on big utility grids, the higher what we call grid penetration, the amount of solar as a percentage to the amount and the size of the grid, we can get enough energy that fluctuations in sun and clouds can really start to push the grid around a little bit with big solar farms. So one of the ways big solar farms are learning to adapt to a grid maybe that's not as stable is the ability to add battery banks into the system. So there's a number of different ways that they can be done. Really, there's two primary ways you connect energy storage into a PV system. There's what we call a DC coupled way and an AC coupled way. And in this case, we're looking at what we call an AC coupled or an AC connected system, where we basically have two inverters. We have the solar inverters, and then we have battery inverters. So the battery inverter or the storage inverter it does a similar thing to the PV inverters, but it handles the battery on its DC side in a different way than we handle the solar on the DC side. It's also going to have a lot of other controls with it. So we can put battery and solar inverters in parallel if they're designed to work together. And what they'll do is they'll end up with a communication system to the utility that'll make decisions based on when to charge the batteries and when to discharge the batteries. And if a cloud comes over, we may push battery power out into the grid to keep it stable. And if the sun comes back out, we may push excess solar into the battery to recharge it. So we can take the solar curves and the outputs of the PV outputs production and change it by using the battery to our advantage. So that's definitely adds a lot of cost, and so that's why we don't see it on all the solar farms. It's a great feature, but it adds a big price to it as well. If the grid needs it, then that price can be totally worth it. So it's, of course, everything comes down to cost. This is just an example of one where it's a wind farm interconnected with a very large battery system. And part of it not only is flattening fluctuations, but it can do a lot of utility frequency and voltage control. And so we can really help to keep stable the grid frequency and voltage by having these battery-based inverter systems coupled with our larger scale renewables. We've now finished talking about the majority of common system applications that there have been out there in the world. PV direct, DC, water pumping, basic type of systems, off-grid, with or without inverters, utility interactive or grid synchronizing systems, and large utility scale power plants. Now, another term that we hear used a lot these days is what we call microgrids. Microgrids are kind of really just a hybrid of all of these things in different ways. Microgrid is not really a well-defined term. It's a term that's used around the world, but it doesn't say exactly what that means, and it doesn't really have a size set to it. So when we think about microgrids, what we want to think about primarily is the idea that we'll have multiple sources of generation, energy storage, loads that are either on-site or distant, utility interaction, and then something that connects them all together in a way that they're all going to work for whatever the application is. And so, sometimes we think of microgrids maybe as an island grid or a village or a small site. Sometimes it's a big house or a big farm. Um, and sometimes it could be towns interconnected with other towns, depending on how we define it. And so yeah, microgrids are used as part of the terminology where all this equipment integrates into, and then has some sort of management control oversight of generation, storage, and consumption. So that's something that we want to think about as we design other stuff and find the right applications for solar here. Now, with these different ideas, another thing that we can do is a term that we use called a multi-mode system. Multi-mode system generally means it's something that is able to be off-grid or grid connected, or often grid synchronizing potentially. And so multi-mode just means this inverter basically is able to operate in different modes depending on the condition, maybe with or without an AC generator, with or without the utility grid, and then being able to operate as a standalone system. What we have with this multi-mode system is an inverter charger that has an input and an output, and sometimes a generator connection separately. It works like a battery-based system, but can also sell excess energy to the grid. So we could take a multi-mode inverter charger and set it into a mode where it'll consume everything on site first, but all excess generation will be pushed back out to the utility grid. Now, normally on systems like this, we separate the AC loads. We'll often have a main distribution and what we call a backed up loads panel. Very similar to what's done with backup generators a lot too. And so with this system, you have an internal AC transfer switch in that inverter. So the inverter has the ability to, if the utility goes down, the inverter opens a transfer switch and it disconnects from the utility. And when it disconnects from the utility, it actually just uses then its battery, its solar, and the inverter to run just the backed up loads. So we put the loads that are our high priority in our backed up panel, and we put loads that we don't need during a power outage in our main distribution panel. And then we have the ability to select whether that inverter sells energy back to the utility grid or does not. And so this is what we would use in a place where we have the ability to sell electricity to the grid, and we have a grid that's maybe not very stable because we want a backup power system, like a backup battery bank. So that's a multi-mode inverter charger. Now, we could do another thing here. Let's say we live in a place where we have the utility connected to our building, our house, or our business, or whatever we're running, and the utility will not allow us to sell energy back into the grid. So we can make our own energy, but we can't export it. There's a number of different terms that are being used out there. Some call it like a zero cell or a grid zero, basically a system that doesn't allow export. We can use the same multi-mode inverter charger where we can use it and have the grid there. If we needed to charge our battery from the utility grid, we could have it to keep the batteries full as often as possible and operate as a backup power system and just not export to the grid. So if the grid was unstable and we were not allowed to export, we could set up a multi-mode inverter charger in a non-export or zero cell selling kind of mode. So that's another way to handle a unstable electrical grid with a utility company that won't allow us to sell. Yeah, we're saying programming, so power goes from the grid but not to the grid. Now, there's another way we can do this without batteries as well. This system is something that is basically the same concept as a zero cell or a zero export system. And in this case, what we're doing is instead of a battery-based inverter, we're using a normal grid synchronizing inverter. And let's say we have a small factory and we make something all day in our factory, and we put this system on our factory because we want to offset our electrical usage. We want to save money, but our utility will not allow us to send excess energy into the grid. Well, what we can do is we can use a system where we have to select the right inverter, and the inverter has to be able to basically turn off the solar or throttle up and down. It's not an on or off. We're able to tell it more or less solar based on what's available. And what will normally happen with a system like this is we'll put CTs or current transducers on the output of the main distribution. So the inverter will only push as much energy into the main distribution panel as the electrical load is. And if the solar output becomes greater than the electrical load at the building, the inverter will throttle down the solar, maybe go to 75% or 50% output, so it never exports energy into the grid. And then one last type I'd like to look at here as well, something that you started to see over the years here is what we call a fuel saver. Fuel saver was made from one company originally, the term, but the idea is that we take a grid synchronizing inverter, similar to any of our grid tie that we discussed with no battery, a grid synchronizing inverter, and what we need to make that inverter come on is a stable AC voltage and AC frequency. So we can use a generator to create our grid, basically, and we can get a grid synchronizing inverter to synchronize with that generator. Now, in order to do that, usually the generators have to be fairly large and good quality, so the voltage and frequency is stable enough for the inverter to stay online because it has a fairly narrow window. So we want to make sure that we have a good quality generator. We also need an inverter that's able to communicate to a generator. So what we see here is this control module. And the control module, what it's going to do is it's going to be able to monitor the loads on the site. It's going to be able to monitor the generator and tell the solar inverters when to ramp up or ramp down. Because what we don't want is a situation where we have too much solar and too little load, and we send energy back into the generator. We could damage the generator by doing that. So we end up with, and there's multiple inverter and generator combination products out there, and multiple companies that are doing this. Usually this is on kind of the 500 kilowatts to, multiple megawatt sizes of systems. Usually we see these in some sort of remote, could be remote towns and villages that have their own diesel gensets. We see them at mining operations or sometimes remote industrial operations where they're running off of generators only. So with the right control systems, we can have a way where we can reduce the load on the generators by paralleling solar without batteries. And the generator still runs 24 hours a day, but maybe we don't need as many of them online at one time. So there has to be an analysis. It often works better in a multiple generator type of situation. So that's another way that we can synchronize solar with a generator source to reduce fuel load in a remote area. Now, of course, there's always other variations of that, but I would say that covers a pretty wide breadth of ways that we have off-the-shelf technology today for different applications based on off-grid, grid-tied, grid synchronizing or selling capabilities, backup power, and scale. It's a very exciting world in the solar industry these days because we can meet so many of these new applications with great products that are designed to do all sorts of things. So thank you so much for spending your time with me today on this webinar. If you want more information, if you like the way we cover things, this was just one lesson out of one of our longer 40-hour or 6-week, 60-hour courses. If you go to our website at solarenergy.org, you can see any of our courses that are available online. This is kind of the lineup of our primary courses, and we also offer a lot of short courses, on demand, and webinar courses as well. So check us out at solarenergy.org, and thank you again for your time.
Well, thank you, Christopher, and thank you so much to our audience for being here for this webinar. We're about to transition into the Q&A portion of our webinar. And as a reminder, to participate in the Q&A, you can just type your question into the box located to the right of the presentation window, or click the Q&A icon at the bottom of your screen. And we'll try and get to as many questions as we can. But before we begin the live Q&A, we've got a couple of questions for you so we can better understand who our audience is today and better answer your questions. I'll read each question and give you a couple of seconds to answer, and then the results will be displayed. And one last thing before we do that is I also want to remind you again about the webinar survey that's available on the right of the presentation window. And if you close that survey, you can reopen it by clicking the icon at the bottom of your screen. And thanks again for filling that out. Okay, so our first question for you is, what is your current role in the energy sector? I'll give everyone about 5 seconds, and then we'll transition. And then we can look at the results. Okay, yeah, that looks about right. So we have a lot of folks coming from an engineering background, project management, project development. So yeah, we hope this was certainly helpful for you. So I guess we've got one more question, poll question for you before we go into the Q&A. Okay, and so what types of solar systems are most applicable to your work? Again, we'll give you about 5 seconds or so. And then pull up the answers for those. Great. So it looks like a lot of the folks that are joining us today are looking into some of those large utility scale systems, as well as some of the more diversified systems out there. Okay. Okay, so now I think we're starting to get some questions in. Christopher, are you ready for our questions?
Yeah, absolutely.
Okay, great. So this first question is great. How can you calculate the size of the PV inverter?
Okay, so when we go to the size of an inverter, first thing we got to do is we have to understand what our application is, just kind of as I said at the beginning there. And because we size inverters different based on whether they're battery-based or utility-connected. And so if we'll just kind of put those into 2 categories for starters. If it's battery-based, it means we have to use the inverter to run the load. And so anytime we have a battery-based system, whether it's an off-grid standalone system or if it's a backup power type of system, then we're going to size the inverter based on two things really. The total connected load, so how many AC watts would the system ever draw? So what's the greatest AC watts that the system could ever consume, because we need to be able to run the entire load and not crash the inverter, of course, by overloading it. So we need to calculate the total connected AC watts in the system, and we would use that as one metric in sizing a battery-based inverter. The other thing we need to understand when we're running battery-based systems is surge watts. So I have my total connected AC watts of the system, or kilowatts or megawatts, whatever it is, and then I also need to know my surge. So if I'm going to be running anything that has a motor or a pump or a compressor, anything that has a starting surge when it starts, I need to make sure that my inverter can handle that. Any battery-based inverter is going to have ratings for not only the constant runtime, but also the surge capacity. So they'll usually break those out as separate values, because battery-based inverters have the ability to surge greater than their normal operating value. So we size it for total connected loads and surge loads of all of our motors. Now, that's in a battery-based inverter. If we're talking about in a grid-tied system where we have solar connecting to an inverter and grid synchronizing with no batteries, if we're not using a battery system, if we're just a normal grid-connected system or utility-scale power plant type of grid-connected system, then we're not using the inverter to run the loads directly because we have the utility there. What we're doing is we size the inverter based on the size of the solar at that point. And so in a grid-connected world, we size the size of the inverter is based on the size of the solar array. In a battery-based world, the size of the battery-based inverter is based on the size of the load that we're trying to run. Hopefully that's helpful.
Yeah, that was great. Now I've got two related questions for you. One person is asking, can you still get power from your solar array if there's no power from the grid? And the second question is can you get solar power from your array at night?
Okay, so if there's no grid, so let's think about our systems again. If I'm grid connected, if I have a normal grid synchronizing inverter with no batteries, then when the grid fails or the grid goes offline, that inverter also goes offline. So if I don't have any backup power, it's a non-battery system, a normal grid synchronizing inverter, there's no power, even if it's full sun daytime, if the inverter's offline. That's why if we live in a place where we have a utility grid that comes on and off a lot, and I want to grid synchronize, then I'm going to need a battery to have a backup system if I want backup. But a normal grid synchronizing inverter shuts off the second the utility goes offline. It's what the feature is called anti-islanding, and it's a way. There's kind of two reasons why we want to shut that inverter off. One, without a battery, it's not a very good backup system because we would be subject to the size of the solar and the loads and all that. So, and two, whenever the utility grid goes down, we don't want to push electricity into a dead line for service and maintenance and those safety purposes as well. So if we need backup power when the grid goes off, then we need a battery-based system. What was the next one then, Michelle, or the other part of that?
Yes. Can you use your solar system at night?
Only with a battery. And so the PV modules, the solar panels, only produce output that are instantaneous to the sunshine. And so if it's a grid-connected system with no batteries, and we get solar during the day, and then we use the utility grid for the rest of that. If we want to use a system at night, then we have to have an energy storage system like a battery bank.
Great, thanks. Our next question is about a specific application. So they ask, what type of solar PV system would you use for a speed traffic camera and a street light?
Okay, so that would be basically a standalone system. If you're looking for, running a device like a traffic camera, for example, you want 24-hour use of that camera system, and so that's going to need to be a battery-based. So it's basically a battery-based standalone system, and then the next, so you would have PV array to generate energy, a charge controller to regulate the charging into the battery bank itself, and then depending on whether those applications, the traffic camera or the any of the other systems you're trying to run, whether those are DC or AC is the next question. If it's a DC device, we could run DC direct off of that system and not have an inverter. If it's an AC device, then we would put an inverter on there to run the traffic cam system as an AC supply.
Great. So here's an interesting question. This person asks, how do you go about using a photovoltaic system for a residential house if there are no current local regulations about grid-connected systems?
And so I guess the question would be, if there's no regulations, then that probably means the utility will not allow you to sell back into the grid. And so that's kind of the question. If the utility has no regulations, then it means they also don't have a contract or an agreement for export power into their utility system. So the first question I would ask is, am I allowed to export power or not? And if, like I said, if they don't have any plans at all so far, it means they also don't have a contract set up or an agreement on how to measure and value the exported power to the grid. So to use residential power in that situation where you can't sell to the grid, it means you're probably into most likely a battery-based grid-connected system where you can use the solar whenever you have sun, and use the battery if depending on whether the utility comes on or off. Now, with that sort of a system, if we're assuming that the utility has no interconnection plan and that you're probably going to have a utility that comes on and offline a lot, then having a battery-based PV system at home that also can use the utility grid to charge the batteries as well. Then we have a kind of a full backup and we can run as much solar as possible, but not export to the grid.
Okay. Next question is, do you recommend micro-inverters instead of regular battery-based inverters?
They're different. So so most of the microinverters that are on the market now are all grid synchronizing types of inverters. And so microinverters are really meant to be utility interactive and utility synchronizing that export out into the grid. Now, there are some microinverters that are designed and are being built now to work in parallel with battery-based inverters, where we have what we often call like an AC coupled or an AC connected system, where we have battery-based inverters and microinverters that work hand in hand. The microinverters aren't going to replace the need for a battery-based inverter in a residential system like that. So I hope that, the microinverters are just not a battery-based device by themselves.
Yeah, I think that was clear. Another person asked, in a situation where you're using a generator, is there any possibility of reverse power flow into the generator?
Yes, there is, and not if you do it right. So that's kind of the question. We want to, if we have a generator hybrid system, then we need to have a control system. And in that slide I showed, there was kind of a control module and some wires connected between them, because anytime we synchronize a generator and a PV system in that type of generator hybrid setup, we have to make sure that if the solar is greater than the generator, or sorry, if the solar output is greater than the load, we need to not let the solar backfeed into the generator. We can damage the generator by sending that energy there. So that's where the control system comes in. The control system is going to measure the load, it's going to measure the solar output, and measure the generator. And so it will know what that difference is between the solar production, the generator production, and the load. And what's going to happen is if the solar becomes greater than the load, then that control system is going to tell the inverters to back down the solar. It's going to say, it's going to throttle down or reduce the solar array output to not allow it to backfeed into that generator. So anytime you set this up, properly, you should never damage a generator, because the control system is there to monitor and measure and adapt to the situation by throttling the solar down. And I really haven't, that's a much further discussion on how the inverter backs off the solar, but a grid-tied inverter has the ability to process less energy if it's told to do so. So it's able just to reduce the output.
Yeah, I think we can see that from some of the questions we're getting and some of your explanations that obviously there's a lot more to the content than what you were able to touch on today.
Mm-hmm.
So we've got a few more minutes for questions, and I'm sorry everyone, there's a high volume of questions. I don't think we're going to get to everyone. But this question is interesting. So they are asking for some of the applications and advantages for using microgrids for rural electrification and rural applications.
Yeah, I guess the applications can be really anything, because like I said earlier, microgrid's not a very well-defined term. It usually means that we're just incorporating this combination of load, storage, various generators like solar, maybe wind, and probably some sort of a diesel or motor generator combined system. And so the concept of a microgrid can really be applied to almost any situation. What you really need to start to understand then is the financial side of this, right? The finances are going to drive everything we do. So we have to look at what are the alternatives. Do we have a utility that's there? Is it stable? Is it unstable? Is it expensive? Is it really cheap? What are we competing against, and at what price point? And that's going to help us drive all of these decisions in, whether is it cheaper for a village or a town or a factory to bring in the power grid? Is it available? What's the cost? And is it stable enough? So we need to weigh all of those things whenever we do any sort of project analysis. Is it cheaper to bring in power, or can I be competitive with a microgrid system that's more, either isolated, like a full-on, total microgrid that's a standalone, or something that's kind of combined, interconnected with the rest of the electrical world out there. So there's kind of a lot to analyze, but yeah, the microgrids can be used for a lot of applications if the finances work out.
Great. And then probably take just a couple of more questions. And so one person is asking, can you use software to help with the design, and what software do people in the industry use for designing systems?
Yeah, so there's a lot of different software packages that are being used throughout the world. And the big differences when you start to look at software is it grid connected or battery based? that's usually where they separate. And most of the softwares either fall into one category or another. And so for grid connected, just a couple that are out there. For utility connected normal systems or big power plant, solar farm type of systems, the one that's very commonly used out in the world is called PV-Syst, and it's really doing the production modeling. It's really focused more on the energy generation modeling of the, basically the angle of the sun, the time of the day, the location, the size of the array, tilts, orientations, all of that. And then there's another really common one that's coming up called helioscope. Those are all kind of grid-tied type stuff. And there's others out there. Those are just some of the big ones that are commonly used. And then if you're looking at battery systems, then those are usually different software packages because they're looking at analyzing the load and the consumption of the site and comparing that to solar power generation, and then trying to use that to size how much backup battery something might need, how big a generator, estimated fuel usage, things like that. So there's quite a few different softwares out there, but the thing to start with is knowing, am I going for a grid-connected design or a battery-based design, and then you would look for different software packages based on that.
Great. And then I think we're going to end with one last question, and then we've gotten a number of questions in here about the efficiencies of systems. So can you just briefly touch on the efficiencies of grid-tied versus battery-based systems?
Yeah, that's a good question. One of the reasons why we see grid-tied systems with no batteries, if we have a stable grid and we're allowed to export into the utility, then a grid-tie non-battery system is the most efficient system that we can buy. We've simplified the number of components by having the solar to the inverter straight into the grid. The solar inverters that are grid-tied solar inverters are so efficient these days that we're looking at 98, 99. Some of them are getting close to 99% efficient. So the market on grid-tied inverters is really like 97, 98, 99% efficiency, which is great. Now, once we go to battery systems, battery-based inverters are less efficient, and so they could be on the bad side, 80, 85% efficient, and on the good side of a battery inverter, low to mid-90s, so maybe 90 to 95%. Some battery inverters might cross 95%, but most of them don't. So there's an inverter loss there on battery-based inverters are less efficient. The efficiency also changes whether it's going DC to AC or AC to DC. So charging a battery bank is less efficient than with that type of an inverter. And then the battery itself has an amount of self-consumption. So there's kind of two things on the battery. When we charge and discharge the battery, we lose efficiency, and that's going to be based on the chemistry of the battery and the age of the battery. As batteries get older, their charge and discharge efficiency goes down. So it's going to start at one point when it's new, and it's going to get worse as it gets older. So the battery has a loss, and then just sitting there, the battery loses a little bit of energy as well. So battery-based inverter or battery-based systems are definitely less efficient, but like everything, they're getting better every year.
Great. Well, as you can see, we're almost at time, so that's going to be the last question we have. Thank you so much for all of the great questions you sent in, and sorry for the ones we didn't get a chance to answer. We really appreciate you being here today. Thanks to our speaker, Chris Sutton, for your time and expertise.
Absolutely. It's a pleasure, and thank you, everyone, for the time.
Yes, thank you so much to our audience. And then lastly, we did get a lot of questions about the presentation. So within the next 24 hours, you're going to receive a personalized follow-up email with details and then a link to today's presentation that you can play on demand. So feel free to watch that again and then to invite your colleagues and peers who might not have been able to watch it today. That is going to be it. thank you all once again for joining us today, and I hope you have a wonderful rest of your day.